Welcome back to ECE 501B. Today, I want to remind you that you have a homework due in 10 days on the 20th of October. And today, what I would like to do is actually finish up Chapter 5. And if we don't get there, I may just assume that we did. And so Wednesday, we will start Chapter 6. Whatever that means. That means that you're on your own depending on how much we do or don't get covered today. And what I want to do today is talk about mainly upper triangular matrices. And you may already be very comfortable with this from a linear algebra perspective or from previous experience with upper triangular matrices, but we'll list a fair number of propositions or theorems related to upper triangular matrices. And these upper triangular matrices provide us with a nice basis. We can immediately start to see what's going on relative to our system behavior or this matrix representation by almost inspection when it comes to us in the form of upper triangular matrices. Proposition 26 talks about upper triangular matrices and invariant subspaces. Proposition 30 talks about the invertibility of our linear map, and that hinges on the fact that we have all of our eigenvalues on the diagonal, but they all have to be non-zero in order for that map to be, or that operator to be invertible. That's what 32 says, is an upper triangular matrix, its matrix representation has all of its eigenvalues on the diagonal. If we have n distinct eigenvalues, where n is the dimension of our vector space, then we can actually diagonalize that matrix, or that linear operator's matrix representation is diagonalizable, which is even nicer in terms of a representation. Now we don't have any of the coupling off diagonal anywhere. And the last proposition just talks about a lot of different equivalences. If we have a diagonalizable matrix, then we have a basis of eigenvectors. We also can think of a direct sum decomposition of our vector space made up of those eigenvectors. That's what we want to cover, and let's start then with an upper triangular matrix, which is a linear operator on R3, and suppose that we say that A now, the matrix representation of this linear map T, and let's go ahead and use the standard basis as our basis vectors for this linear map or operator. And let's say that the matrix representation in the top row is 2, 3 minus 1, 0, 4, 1, and 0, 0, 5. Without deriving anything, let me just write down what the you should be able to now tell me what the eigenvalues of that are. Those are along the diagonal. So we have 1 eigenvalue is 2, and its, let me represent its eigenvector as W1. The eigenvector has to be invariant relative to that eigenvalue, and this one then is really just the x direction if we were thinking in three-dimensional space. The second eigenvalue is 4, and its eigenvector W sub 2 is proportional to the vector 3, 2, 0. And the last eigenvector, or I'm sorry, last eigenvalue is 5, and its eigenvector is now proportional to 2, 3, 3. And you should be able to go back and verify that, but those eigenvalue-eigenvector combinations need to satisfy the eigenvalue-eigenvector equation. A W is equal to lambda W with the appropriate subscripts. And let's just see what happens relative to our basis vectors and this matrix representation of a linear operator. Here we have V1 is 1, 0, 0. That's our first basis vector. V sub 2 is 0, 1, 0. And V sub 3 is 0, 0, 1. What happens when we operate on our first basis vector with this linear map A? And the linear map A is 2, 3, minus 1, 0, 4, 1, 0, 0, 5. And now it's helpful to think about matrix vector multiplication in that one way of what's this particular vector doing? It's actually saying, let me just take the first column of that A matrix, and that's all I'm going to take as my product. Meaning this guy, this AV1 product, is now going to yield a vector 2, 0, 0, and I hope that it's clear that that's lies in the span of our first basis vector V sub 1. And there's only one vector needed in order to represent the result of this operation A, or this operator A, operating on W1. If we, or V1 in this case, our first basis vector. If we now operate on V2 with the same A matrix, now what do we get in terms of a result? So this is just pulling off the middle column, the second column in the A matrix, and that's now 3, 4, 0. But we can represent this vector, 3, 4, as falling in the span of which of our basis vectors? So now you should see that as long as we have vectors V1 and V2, then we can represent this eigenvector. And so now AV2 lies in the span of two of our basis vectors, and you can sort of see this building up of dimension or vectors as we step down relative to this upper triangular matrix. So as we get further and further into, so to speak, columns of this upper triangular matrix, it requires more and more of our basis vectors to represent that vector, or that vector result lies in the span of more and more basis vectors. And finally, if we look at AV sub 3, we're now pulling off the last vector in the A matrix, which is minus 1, 1, 5, and that we can create as a linear combination of all of our basis vectors. We have minus 1 times V1 plus 1 times V2 plus 5 times V sub 3, or this is now in the span of V1, V2, V3. And that idea may appear or start to be seen in several of our developments in today's class. We're dealing now with upper triangular matrices, and I want you to just be thinking about what actually happens as we walk through this matrix vector multiplication or these eigenvalue-eigenvector relationships for upper triangular matrices. Let's look at some observations or maybe some quick notes on the matrix representation. Of an operator. If we're dealing with an operator, what do we know about the matrix representation of that operator? It's square. What else do we know about an operator in terms of the vector spaces? It's the same. We have the same vector space in the input vector space and the output vector space. And if we have that vector space being the same, we really only need one set of basis vectors. And what we want to do then is, if we have this square matrix and we only have need for one set of basis vectors, it might be nice to pick a nice or a good set of basis vectors. And now maybe I will try to define what I mean by good or efficient or nice. We are looking to find good or efficient basis for our linear operator or for the system. The claim that we will make is that a good basis is one where the matrix representation of that linear operator is what we could call simple. And the meaning of simple, throwing quite a few words around that we use on a daily basis, but now we're implying particular characteristics or properties of those. Simple is going to mean lots of zeros in the matrix representation. So we're trying to find basis vectors or representations of this linear operator that will provide us with as many zeros in that matrix representation as possible. And the upper triangular matrices provide us with a pretty good start on putting zeros into our matrix representation. Let's now go back to what we've already learned. We've already found that we have some results we've already developed. Are sufficient to show that for a finite dimensional complex vector space, FDCVS, there is a basis where the matrix representation of T has a particular structure as follows. The matrix representation of T has a lambda, and underneath that lambda, they're all zeros, and everywhere else, I'm going to be using this star to mean that that represents anything arbitrarily can be in any of those other locations. This is what I'm defining to be arbitrary. And now let's remind ourselves of these previous results. But now I'm saying what we've already done so far this semester is we can rewrite these linear operators or find a set of basis vectors that will allow us to at least produce zeros in the first column except for the very first entry, the 1, 1 entry. Let's justify that. One is that previously we proved that this linear map, and in our case a linear operator, has at least one eigenvalue lambda, and I think that's what we finished our last lecture discussing or showing. We previously proved that T has at least one eigenvalue lambda and the eigenvector associated with that lambda, and an associated eigenvector, let's say V. That was actually theorem 521. For a finite dimensional complex vector space, we know that it has to have at least one eigenvalue. And we have also talked about, previously proved, maybe earlier than chapter 5, previously proved that if we have one vector, let's say it's one of our basis vectors, we can extend that set of vectors to form a set of basis vectors. So we previously proved can always extend a linearly independent list of vectors on the finite dimensional complex vector space. And by extending, I'm meaning we can extend it up to form or find n of those vectors if the dimension of our complex vector space is n. And one way that we could maybe see that is, in general, what does the matrix representation of a generic linear operator look like structurally in the first column? In general, not what we just said, but in general, if I said, give me the matrix representation of a linear operator, and I said, just tell me what's in the first column, I'm going to assume that what's in the remaining columns is arbitrary. What do I know is possible in that first column? Or these are going to be the weights on all of our basis vectors in that particular vector space, which means in general, what do we know could happen in that first column? What's the first element doing? let's say A11. That's now weighting the first basis vector in our set of basis vectors. What's A21 doing? So we have A11, let's say V1, plus A21 times V2. If this is a generic linear map, a linear operator, then we are going to generically have A's awaiting some linear combination of all of our basis vectors. The first column is going to be made up of some arbitrary combination of the n basis vectors. So this is, in general, going to be a fully populated or a fully non-zero column. But in our case, when we're talking about this, we've now restricted attention to a little more specific case. In our case, we now know that every linear map on a finite dimensional complex vector space has an eigenvalue lambda and its associated eigenvector v. So that if somebody now says, oh, we have TV, then we might have TW1, TW sub n minus 1. We're assuming now that we have n vectors. We now want our matrix representation, which is A11, A21, AN1, A12, A22, AN2, etc. These are now describing how we are weighting our basis vectors. We have AV, or TV is equal to V, then W1, W2 up to W sub n minus 1. And out here we have A sub 1n, A sub 2n, down to A sub n. And if this is our particular A, then we know if V is an eigenvector, then our particular A has a much more specialized first column. If V is an eigenvector and it has an eigenvalue lambda, what do we know has to be true for the A matrix? TV is lambda V. So everything below that first entry, or first element in our A matrix, is 0. If, indeed, lambda is an eigenvalue and V is an eigenvector. So if we hit V with our linear operator T, then we know we have to be living on that same vector V, and so it's a scaled version of V, and it's scaled by the eigenvalue lambda. Now remember what we have. And let's say I'm going to switch this to J because I am better at making J's than I am K's, although you'll probably argue that with me. But the Jth column of this matrix representation is actually the result of applying our linear operator T to the Jth basis vector. And in our case, our first vector in our basis is in fact the eigenvector v, and we can think of that v in terms of being expressed as a linear combination of our basis vectors, and has the following representation, where v now needs to be some linear combination of v, w1 plus w2 plus something w sub n minus 1, where all of these are our basis vectors. And how do we weight those basis vectors to produce v on the left? This is a trivial question. How do I get v back as a linear combination of v, w1, w2, w sub n minus 1? So we should have 1 weighting v and zeros everywhere else. And we know that TV, then, if v is an eigenvector, then it has, or it satisfies this eigenvalue-eigenvector equation. And the only way that we can now weight v with one coefficient lambda is to force all of our other coefficients that weight our basis vectors to 0, or that is, now we have a11 equal to lambda and a sub ij equaling 0 for j going from 2, 3, up to n minus 1. Or in this case, I guess I'm already in the matrix, so it's a dimension n, so let me say that that's up to n. And that's now forcing that structural property on our A matrix. Lambda is only going to be weighting our first basis vector, which is v. Oh, sorry, I have too many i's and j's. So it's now should be j1, because I need to be incrementing down the rows in the first column. Thank you. So it should be a sub j1 equaling 0 for all the coefficients that would be weighting the w1, w2, w sub n minus 1 of our basis vectors. And that says then that we can actually find, using just one eigenvector, a representation where at least we have all zeros below the very first entry. What we want to do is probably do better than that. We want to now find more zeros in our matrix representation. And we can, as you would have expected, since we're talking about upper triangular matrices. But we can do even better than just having our first column filled up mostly with zeros. An upper triangular matrix by definition is one where all of the elements below the diagonal are 0. So that now we have this lambda 1, lambda sub 2, down to lambda sub n. We have zeros below the diagonal and possibly any arbitrary elements above the diagonal. So now, not only do we have all zeros below the first element in the first column, we now, as we move over to each subsequent column, we have all zeros below each of those diagonal elements. And what we want to do now is learn a little bit more about those particular matrices. Let's now look at proposition 26, which starts making equivalents or certain statements equivalent to each other. If T is a linear operator on a vector space V, and we have a basis V1, V sub 2, up to V sub n, on our underlying vector space V, which is the same vector space for our input vector space and our output vector space, the following statements are equivalent. A, the matrix representation of T with this basis V1, V2, up to V sub n is upper triangular. And I may start abbreviating that as UT. So we haven't really said anything yet. We've just established a linear operator and a basis. But now we're saying that the matrix representation in this basis is upper triangular. Now an equivalent statement would be that T, the linear operator operating on a basis vector V subscripted with L, lies in the span of V1, V2, up to just V sub L, not any further than L in terms of the basis vectors. And that's true for each L in our entire set of basis vectors. A and B are equivalent statements. We have a third statement that's equivalent to both A and B, and that is that the span of V1, V2, up to V sub L is invariant under T, again, for each L from 1, 2, up to n. And what's it mean if I have invariance of my linear operator? If I have an invariant map, linear operator, that's invariant on this span of vectors, then if I hit, or if I have any vector that's in that span, what happens when I operate on that vector with this linear map T? Then we are not necessarily scaling anything per se, but we're saying that if this span is invariant, then when we hit it with T, anything that's made up of these L vectors is going to return to some other linear combination of those L vectors. It's invariant. It goes right back into those L vectors. Meaning, if we started with a vector in the span of V1, and operate on it with t, then the only place we can go is v1 or some linear combination. So now we're on that line. But if you give me a vector that is in the span of v1 and v2, let's call it z. Well, maybe that's a poor choice. Let's call it w. W is a1 v1 plus a2 v2. Then if we operate on it with t, we're going to go to cv1 plus cv2. It's going to be invariant to that subspace, or the subspace spanned by v1, v2. And we'll just keep seeing that same behavior if that linear operator is invariant relative to this span of basis vectors. So let's see if we can show the equivalence of these three statements relative to having a linear operator and this particular set of basis vectors v1 through v sub n. And one way to do that we've shown is A implies B, B implies C, C implies A. Let's do it a different way. Let's show that A and B are equivalent. So if and only if, essentially, and let's show then that B and C are equivalent. Then we can get anywhere we want if you tell me that you know one is true, if they are equivalent. Here's our proof then. Let's start with, we'll say, part I of this proof, and that proof is to show the equivalence of A and B. So A implies B and B implies A. Let's show that A implies B. And A was, we're starting with an upper triangular matrix, and B said that we have sort of this nesting behavior of our spanning set of eigenvectors. So let's see if we can sort of nest these basis vectors in terms of how they work if we have an upper triangular matrix. Let's now consider the matrix representation of this linear operator T. In this case, the nth column of the matrix representation of T is the expansion of T v sub L in terms of our underlying set of basis vectors, v1, v2, up to v sub n. That's the definition of the nth column of the matrix representation of T. We take the nth basis vector and map it, or apply the map T to that. And then that needs to give us some linear combination of v1, v2, or the basis vectors. But what do we know if we're given A? If our matrix representation is upper triangular? What does the nth column of that matrix representation look like? The nth column of an upper triangular matrix and now sometimes it helps to just try to draw this. There's our nth column of our matrix. And what do we know about that if this matrix representation is upper triangular? So here are our first L elements in that representation, and they can be anything, correct? But what do we know about what lies below that, which is the remaining n minus L elements? Those are all 0. Or we could now label this as A1L, A2L, down to A sub LL, and then we have 0 below that. And what does that say? Well, now this tells us our weights on our basis vectors. This now says that A1L weights V1, and A sub 2L weights the second basis vector. And we just keep going. A sub LL weights V sub L, and then we have 0 weighting V sub L plus 1, and we continue with zeros for weights all the way down to V sub n. And what does this tell us then about how we express T V sub L? Or what vectors do we need to express this result of hitting V sub L with this linear map T? How do we write that in terms of basis vectors? This means that T V sub L is expressible in terms of what basis vectors? Well, I see we're weighting V1 generically. We're weighting V sub 2 with A sub 2L, but we only go as far as V sub L to allow for any possible representation of T V sub L. And what does that mean in terms of where T V sub L lives? In what span of vectors? That lives in this collection, or the span of these vectors, V1 through V sub L, for any L. And that's statement B. Statement B is T V sub L lives in the span of V1 up to V sub L for each L. If we started with L equal to 1, then T V sub 1 lives in the span of V1. If we use V sub 2, then T V sub 2 lives in the span of V1, V2. And we showed that at the early part of today's class, how that can be seen. We've now shown then that A, upper triangular, implies B, this span relationship. What about B implying A? We're trying to show the equivalence of A and B. B says that TV1 lives in what span? What is statement B? TV1 lives only in the span of V1. That's statement B. That was L equal to 1 up to N, right? And if we had TV sub 2, that now lives in the span of V1 and V sub 2. Statement B says that we can just keep going, and if we go all the way to V sub L, where L can go from 1 to N, so all the way up, this now result has to live in the span of V1, V sub 2, up to V sub L. But if that's the case, remember how we can sort of write a vector that lives in the span of other vectors. You could now say, oh, TV1 must equal, if that equals or lives in the span of V1, then that's some scalar version of V1, where now I'm just going to call my scalar alpha. Is that consistent with the first row of statement B? If TV1 lives in the span of V1, then there's a linear combination of V1 that has to be true, that has to create TV1. What about TV sub 2? It now lives in the span of V1, V2. And let me be sort of selective with how I label my weightings. Now I have some linear combination of V1 and V2. If TV2 is in the span of V1, V2, and now let me pick this to be alpha 1, 2 and alpha 2, 2. It just has to be some linear combination of V1 and V2, and now I'm just going to label that combination with scalars alpha 1, 2 and alpha 2, 2. And I can say TV sub 3. Well, that's some linear combination of V1, V2, and V sub 3. And let me just pick these coefficients. Now this is, let's say, alpha 1, 3. Some scalar. This is now some scalar multiplying V sub 2, and this is some scalar multiplying the third basis vector. And what happens? I can just keep doing that and doing that, and TV sub L now is alpha 1L V1 plus alpha 2L V2 plus alpha LL V sub L. And what do those alphas do if I put them into a matrix? I had alpha 1, 1, and I didn't have anything else with a 1 in the second entry, coefficient or subscript-wise. What about the second column? That's made up of alpha 1, 2 and alpha 2, 2, and nothing else. So I have zeros below that. And I had alpha 1, 3, alpha 2, 3, alpha 3, 3, and zeros below that. And I just keep going all the way to alpha 1n, alpha 2n, all the way to alpha nn, since L was allowed to march between 1 and n. And what's this matrix representation of this linear map T, or linear operator T? Well, that looks upper triangular to me, and that's what we were trying to show. We were trying to conclude that B implies A. And in fact, we now can see that this matrix representation of this linear operator T is indeed upper triangular. When we force upon that linear operator this nesting type behavior of the spans of these vectors, V1 through V sub n. We've shown then that B implies A, and we just recently showed that A implied B, so now we've shown that A implies B and B implies A, and now we can conclude that the statements A and B are equivalent. That was part one of this proof of showing these three statements are equivalent. If we look at part two, now we want to show that B and C are equivalent statements. And let's mix it up a little bit. Suppose that we now say, well, let's show that C implies B by a contrapositive argument. Contrapositive, so now we look at the position and we basically we switch positions and we take the negative of those. So that now what this contrapositive argument is going to allow us to do is now we can assume, so we're trying to show C implies B. What we do is we say, oh, the result, we take the negative of the result and show that that implies the negative of the antecedent, or the C in this case. So now we assume not B and show that not B implies not C. And that would be a contrapositive demonstration of C implies B. That's our contrapositive proof technique. And now we want to start then with not B, which said B was we have this nesting property of invariance of these basis vectors. If we now look at T v sub L, now we know that that's not supposed to live in the span of V1, V2, up to V sub L if we're assuming not B. And that's true for each L. That's not B. B was TV sub L is in that span, and we say let's not that statement. And this says then the span of V1, V2, up to V sub L can't be invariant, because now if we, with this assumption, TV sub L throws us outside of V1 through VL, we have to pick up or use other basis vectors to represent TV sub L. And so that's not being invariant. So we can't be invariant because T acting on a vector in this span of V1, V2, V sub L actually produces a vector outside of or not in the span of V1, V2, V sub L. So we've now shown that that collection of vectors, V1 through V sub L, is not invariant with respect to T, and that was statement C, that it was invariant, and we've just shown it's not invariant. So this is now our contrapositive argument. We started with not B, and we showed that that implies not C. And that now says that, oh, C implies B. Now we want to go one more step and show that B implies C. Let's do this more directly. If B, and what is B? B contains this nested property of invariance. If B, then C is really the, by definition, of invariance. Meaning B tells us that if we have TV1, that's in the span of V1. TV2 is in the span of V1, V2. And we just keep going, where TV sub L is in the span of V1, V2, V sub L. And that's an invariance property. Therefore, V1, V2, up to V sub L is T invariant. Which shows that if B, then C. And we just showed by the contrapositive argument that C implied B, and now we have shown the equivalence. B implies C, C earlier implied B, and we're done then with showing that those three statements are in fact equivalent. That if we have an upper triangular matrix, then we have this nesting property of spans, and we have this invariance property with respect to our eigenvectors v1 through v sub L, or v sub n. Let's look at some more statements relative to these upper triangular matrices. And again, in this discussion, I will probably just start using UT to mean upper triangular. And we may not have time to go through the proofs, so I will refer you to the book by Axler for the proofs. Theorem 27. Theorem 27 is, let's start with a vector space, V, and we are assuming that this is a complex vector space, or we're now operating with elements in the field of complex numbers, a complex vector space. And let's now have a linear operator on that complex vector space V. Then there is a basis of that complex vector space V, where the matrix representation of this linear operator T has upper triangular form. Now that's actually a fairly powerful theorem. What does that say? If you're working on a complex vector space, you can always find a upper triangular representation, a basis that will produce that. But the caveat or the constraint is complex vector space. This is not necessarily true if we're dealing with a real vector space. We may not be able to upper triangularize a matrix if we're dealing on or working with a real vector space. This is not necessarily true for real vector spaces. And let's just sort of think about what we're now saying in both situations, with complex vector space and a real vector space. Think about the form of the matrix representation when we're operating over a complex vector space. That says that this matrix representation now has a representation that is upper triangular. The fact that the first column has only one non-zero element, that's the lambda 1, means that the first vector of the basis is what kind of a vector? It's now scaled by lambda 1, and what have we been scaling with lambdas? So that first basis vector has to be an eigenvector, doesn't it? So the first vector of the basis is an eigenvector. Of our linear operator T, and it has eigenvalue lambda 1. Meaning now we have this lambda 1, lambda 2, lambda sub n. We have zeros below, arbitrary up above the diagonal, and now we have 1, 0, 0, 0, and that's now lambda 1, 1, 0, 0. So now we know, if we were thinking in terms of matrix representations, if we start with an upper triangular matrix, that very first entry, the 1, 1 entry, is in fact an eigenvalue. And the first basis vector is an eigenvector. But we've learned that there are cases when we're dealing with real vector spaces, if T, our linear map, may not have an eigenvalue. When were we assured that it had an eigenvalue? When we were dealing with complex vector spaces. When we have real vector spaces, we could be doing rotations. And that's not going to preserve this direction when we operate on a vector with a rotation. So if T has no eigenvalues, and that's possible for reals, then it must follow that T, our linear operator, has no upper triangular representation or matrix form. If you're restricting then to a real vector space, we can't necessarily upper triangularize our matrix representation. We can't find basis vectors to do that. Let's look at another proposition. Suppose now that we have this linear operator T, and this linear operator has an upper triangular matrix representation. If T is an operator on a vector space V and has an upper triangular matrix representation, then this linear operator T is invertible if and only if, so this is going both ways, if and only if all the diagonal entries of the upper triangular matrix are non-zero. So if you've now found a basis where you've been able to find an upper triangular matrix representation for this linear operator, you can now look at these diagonal entries, and as long as they are non-zero, you know that that linear map can be inverted. Question? So this is now saying exactly, well, we're going to get to that in just a little bit. We now are saying that if all the entries are non-zero, that means that all of our eigenvalues, which are on the diagonal, are non-zero. So we have non-zero eigenvalues for this linear map. So we don't have a zero eigenvalue if, in fact, our linear map is invertible because of this similarity between injective, surjective, and invertibility of an operator. So let's look at what proposition 530 leads to in terms of another proposition. Proposition 530 leads to one of the key results in all of Chapter 5. And that's the following, which is proposition 32. Given this linear operator T on this vector space V, which has an upper triangular representation on some basis. So that's given. We have this linear operator T, and it has an upper triangular representation on a basis. The eigenvalues of this linear operator T are the diagonal entries of the upper triangular matrix. But right now we haven't said anything about invertibility. We're just saying we could have zero eigenvalues. They're just on the diagonal. Given T, which has an upper triangular representation on some basis, the eigenvalues of T are on the diagonal of that upper triangular matrix. If we wanted to look at showing that, let's now take that basis to be V1, V2, V sub n. We have some basis that gives us this upper triangular representation of this linear operator. So take V1 through Vn as the appropriate basis. Or that is, now we have the matrix representation of T with respect to v1 through v sub n is now this lambda 1, lambda 2, lambda sub n. We don't know what's, or we don't care what's above, but we are forced to have 0 below the diagonal. We now have this matrix representation. Let's now take lambda to be some scalar in our field of numbers F. And we now can look at the matrix representation of t minus lambda I over that same set of vectors, v1, v2, v sub n. That's now lambda 1 minus lambda, lambda sub 2 minus lambda, lambda sub n minus lambda, arbitrary up above, and 0 still down below the diagonal. And now we can start showing this relationship. Remember, eigensolutions, meaning solutions to our eigenvalue eigenvector equation, TV is lambda v. Remember, the eigensolutions are associated with the null space of t minus lambda I. Which means we want t minus lambda I to have a non-trivial null space or to be non-injective. Which means we want t minus lambda I to be non-injective. If it wasn't, we would have a trivial null space. And this gets back to what was just commented on before. But also remember this equivalence between different relationships of an operator. Also remember that for operators, if that operator is injective, that's only true if that operator is also surjective, which is equivalent to that operator being invertible. Or in other words, this is equivalent to saying we want t minus lambda sub I to be non-invertible if we're wanting it to be non-injective. Because those three are equivalent. Our previous result which was proposition 30, shows that if we have this upper triangular matrices, or that shows that upper triangular matrices are invertible, if and only if we have non-zero elements on the diagonal. But we actually want this to be non-invertible, so we want some of these entries on our diagonal to be 0. Thus, lambda equal lambda 1, lambda equal lambda 2. All of those values for lambda are the values that will make t minus lambda I non-invertible. That will make you have a 0 on the diagonal if you have any of those lambdas equal to lambda 1 through lambda sub n. And hence, those values of lambda have to be the eigenvalues of our linear map. And what I will suggest is that you look at the last part of chapter 5, which is dealing now with even more specialized or nicer matrices, diagonal matrices. And if that's the case, then we have basis vectors that are the eigenvectors of T, and you might look at the following propositions: 38 and 41. And make sure that you're okay with those, and what you can also do with this under real vector spaces. And as I promised at the beginning, we'll pick up with chapter 6 on Wednesday. I'll assume that you're now able to go on through and look at these results for diagonal matrices.